Another way to derive the wave solution is by finding the dispersion relation, which is the relation between frequency and wavelength. Finding the dispersion relation is a more general way of dealing with these equations to find waves and instabilities and the general behavior of hydrodynamical systems. If we consider again the original equations and decompose the density and the velocity into its Fourier modes, so we have that any quantity psi is going to be given by its complex amplitude and the exponential of minus I times omega t plus kx. Omega is the frequency, t is the time, k is the wave number, and x is the coordinate. So substituting this into the equations, this Fourier decomposition is very useful because then the time derivative, when it operates on this quantity, is going to give you simply minus I omega. And the spatial derivative is going to give you simply minus ik. So this is a way to replace the time derivatives by I omegas and the spatial derivatives by iks. And then you have a differential equation turning into a simple algebraic equation. These two systems are equivalent. Now, if we isolate u hat in the second equation and substitute it on the first, this is what we find. We find omega squared is equal to k squared times the square of the sound speed. So omega is equal to plus or minus k times the sound speed. If we plug this back into the Fourier mode, substitute omega here, this is what we get. So the system is Galilean invariant over the transformation. If you turn x into x plus or minus CST, you have the same system. So this is a wave. It's ik times this x coordinate in here. So that's a sine and a cosine. So it's a sinusoidal if k is real. So this is a wave propagating with velocity cs, which is the sound speed.